crap.
This problem is a very famous problem. In fact, Leonhard Euler lived in this East Prussian city called Königsberg. Here's my notes down here. The Pregel River flows through the city, forming two islands, A and D. Okay. At the time that Euler lived, there were 7 bridges. The bridges are the little letters A, B, C, D. And people would go out on Sunday afternoons for a walk around the city, and the question came up, could I start anywhere, let's say D, and cross every bridge once and end up back at where I started? And people tried to figure it out, and they would take different paths walking each Sunday, and guess what happened? They couldn't figure it out. So they turned to Leonhard Euler, very famous mathematician who did all kinds of things. And his approach was actually the beginnings of what has turned out to be graph theory. And graph theory, when they first invented it, he kind of started it with this problem. It had no real purpose other than to figure out if you could walk across each bridge one time. But it evolved into something that, if we didn't have it today, we wouldn't have a whole bunch of things that we have, including the internet. And even the phone systems that we used to have, and now is all gone to cell phones anyway. Does anybody have a landline? No. I do. But...
My parents
So,
do.
let's get some vocabulary. A network consists of points. Sometimes we call those points vertices or nodes. This PowerPoint is all available to you. You do not need to write this down unless there are ideas that aren't in the PowerPoint. Then you'd write them down, but I've made it available to you. Okay, so we've got these points. They're connected by curves known as edges. So, frequently, mathematicians and others will take a real-life problem and convert it into a network diagram. And the network diagram then becomes easier to work with. So, capital B is the land mass on this side of the river. It's the whole thing. Capital A is the land mass in the island. D is the other island, and C is the other side of the river. Okay? Each of these edges are what? Bridges that connect those. Okay? So you see there's a little bridge labeled little c connecting A and D. Well, that's A and D. It must not be, it must be E. Yeah, C is up there. So do you see bridge C connecting A with C? And then here's bridge D connecting A. That's this bridge here. Everybody see how we've translated it into... That makes sense? So, the land masses are the capital letters. The bridges are the small letters, which are the edges connecting those landmass points or nodes. Okay? A path in a network is a curve traced by following a sequence of edges in a network where no edge is retraced. Not all edges need to be traced, but the vertices can be revisited. So you can't go over a bridge twice, but you can go back to the same landmass twice. We say that a network is connected if every pair of vertices can be joined by some path. Now here's the one we're going to be dealing with. An Euler path is path that traverses each edge once and only once. We say a network is traversable. That's not a math word. Does anybody know what that means? Traversable. Can be traveled. That's what it means. Can be traveled. A network can be traveled if and only if it has an Euler path. Okay, which means we're going to go across each bridge once and only once. All right, so on a piece of scratch paper, I would like you to draw this and then see if you can put your pencil down at one of the vertices and without going over one of the lines more than once, go all the way through the network. Travel each one once, okay? But nothing twice. Can you do it? Can somebody jump up to the board and come up here and
oh, I'm kind of doing it turned around. Is that
okay, that's all right.
Oh, that didn't look so good, but
Are you convinced that she did it?
Mm-hmm.
Yep.
Do it one more time. Sorry.
and you can do it different ways, but that's the way I can really.
I did it differently.
Okay,
Okay.
yeah.
I'm not going to fully connect the lines so that you can see it. But I would like this.
Did she do it?
You don't have to end up in the same place.
Nope.
You do not have to end up at the same place, but you have to go across every bridge once, but no more than once.
So to get back to the starting place, you have to cross the bridge again, though.
Okay?
It's actually a proof formula for these to determine if it's
All right. Are these networks traversable? Can you go across each one of these once? In other words, can you put your pencil down like they did up here and draw either of these two? Try it. Give it a try.
I don't know how to do it, but I can already tell you that the one on the left is possible.
The one on the left is possible.
Uh-huh.
You don't know how to do it? Well, then prove it.
You said he has a formula.
Yeah, it's the number of.
Okay, shh. Kaya. E, G, E, D, A. Okay, A, B, E, D, then back to B, up to C, down to D again, then to A, and then to F, and then to E. Okay, if you go in that order, she just wrote her path. That's how you designate a path. It's got letters on it. You just do the order you go in. She could have stuck the G in there, but since she went through it, we all know the. Okay? Is everybody with us? Anybody get this second one?
It's not possible.
You don't think it's possible?
I would be willing to bet money.
You're pretty sure you got it. Let's, Shannon, give us a try here and see what.
How much money you willing to bet here, bub?
I'm curious.
Alright, so I did C2. Up. Then you go down. Then you come over here. Then you go back down. Then you go up. Then you go down. Wait, you don't have a lot of your Oh no! Just kidding.
We could try some more. We're running out of time. Let's talk about this. Is everybody with me? Every node can be designated as odd or even. 1, 2, 3, 4. The degree of this node is 4 because it's got 4 curves or edges coming into it. What that means is if I start here, see if you can follow this logic. If I start here and leave on one of them, I could come back on another one, and then if I leave, I've got to come back. So if I start on an even, I must end at that same place. Does that make sense? Think of just going around a square. This has got 2, 2, and 2. If I start here, I've got to end there, right? However, if we take one like, so if I start at F, I've got to end at F, right? If I start at D, I've got to end at D. If I start at C, I've got to end at C because they're all even. Does that make sense? But notice, E is odd. If I leave there, then I can come back, guess what? I have to leave again, therefore I can never end where I'm starting. Well, that means if I've got an odd and I start at the odd, I can't end back there. I've got to end somewhere else. But if I end somewhere, where is it that I'm going to end? Well, I can't end at an even. Because an even means I leave it, come back to it. Maybe several times, but... So, you'll notice I've got an odd here and an odd here. She started at A. Where did she end? Look at her network. At E. Well, that's because you can leave it, then you can go through it again, but then you can't go back to it. Where do you got to go back to? You got to go back to one that maybe you went through, but when you come into it and you don't leave it, it's going to be odd. Does that make sense? So here's the rule. A network is traversable when it has all even, in which case you can start anywhere you want and what? And end up at the same place. Or if it's got exactly 2 odds and you must start at one of them and end at the other one. Every other network is not traversable. Does that make sense? So, we look over here. Odd, odd, odd. All of a sudden I know this is not traversable. Because I could start here and end here, but what am I going to do here? Does that make sense? So I don't even need to check these other ones.
So what's that called again? C is a node? Is that what
A node. Mm-hmm. Yep. So you have to have all nodes are either all even, in which case you can start anywhere and end at the same place, or 2 odds and you've got to start at one and end at the other. And then they're traversable. Otherwise, you can't. Now, there's one other relationship. And we've run out of time. Is there a relationship between the number of vertices, edges, and regions of a network? So if we count the number of vertices, edges, and regions, we get 4 regions. It says be sure to count the unbounded region. That's the region that's out around the whole thing. So 4 regions. If you count the vertices, we get 7. And if you count the number of edges, that's the segments or curves, we get 9. Is there a relationship between them? Yes, and we've run out of time. So I'm going to just let you pull up the, would you pull up the PowerPoint? Your first thing you want to do is go and do this little exercise. The one we just did was 7, 4, and 9. Do it for 1, do it for 2, do it for 3, and see if you can discover the relationship. If you get bogged down, don't spend more than about 15, 20 minutes. Google Euler's formula for networks. Euler, does everybody know how to spell Euler? Doesn't sound like it looks.